Moment curvature, we talked about the key. Moment curvature relationship is very, very important. Curvature, we talked about what is curvature. We said that this is the ratio between the radius of curvature, and from this one we can determine these two values, concrete strain and depth of neutral axis, help to determine the curvature. Any combination, or in fact every combination of the of the neutral axis depth and strain can give you one curvature value, because it's the angle. So angle depends both on the neutral axis depth as well as the strain. The only thing is that only some of those values are valid. All values are possible, but only some of those values are valid. And the valid value is the one which gives us the stress resultant axial load equal to the external axial load. So if you change the neutral axis depth or change the strain, and it gives you a load value, axial load value, which is not matching with the applied load, then that is not a valid combination of the strain and neutral axis depth, and that creates the problem. So for a given axial load, let's say 0, in case of a beam, we have to find a combination of the neutral axis depth and strain which will give us 0 resultant loading. That means tension and compression must balance, and at that point whatever moment is given is the moment curvature for that value. Then we try another such combination. So there will be many such combinations for neutral axis depth and strain. For each neutral axis depth, there will be one strain which will give you one condition. For next neutral axis depth, another strain which will give you same condition. So we can plot those to get the whole curve. And that is what we were talking about. And so this is a particular location where the first cracking comes, where the concrete strain is equal to, or the strain at the bottom is equal to the concrete tension strain. That is one point. Second point is when the steel strain is equal to the yield strain. That is another point. And then another point is when somewhere we have failure of concrete. So you can plot these control points on the moment curvature curve. And this one, actually, if you plot it completely, this will be something like that. And this is when crushing comes first. That means if you have too much of steel, you follow that curve. If you have few amount of reinforcement, you follow that one. So as you can see very clearly that the shape of the moment curvature curve matches the predominant failure material. So if it is steel failure, it looks like a steel stress strain curve. If it is a concrete failure, it looks like a concrete stress strain curve. So that is, and sometimes it is in between. For some portion steel governs, some portion concrete governs. So you need to draw that whole curve when you deal with that. So I don't want to read anything. You can read all of that. Let's look at the stress application now. So typically, a moment curvature curve should look like this in reality, where we have combinations of failure. In fact, there is no single rebar in the column. Let's say if it's a column, this is a column. There are many reinforcements. So each yielding of each rebar will create a certain point or certain change in the curvature. So every time one part of the section fails or one rebar yields, the curve changes. So you can see those changes coming from failure of various, not failure, reaching of various rebars into the yield level. And then here, at that point, the concrete starts to fail also. Now, this left side data is very important. This image is coming from Section Builder, the program that I'm going to give you. So, what is important is what you see on the left hand side. Please look at these. Can you read this left hand side? Right? Yes or no?
Yes, sir.
Yeah, okay. So, first of all is moment angle. This is very important for a cross section. What direction of bending are we looking at for the moment curvature curve? Because the cross section can bend in any direction with respect to the x-axis. So this is the angle from the x-axis where you want to bend it. So if angle is 0, that means the column is bending about the local y direction along the x-axis. If the angle is changing, then the cross-section is bending about different angles. So every time you change the angle, you will get a different moment curvature curve for a general section. For circular section, it will always be the same, right? Just like moment interaction surface. Second item is axial load. That means how much axial load on this section, because as we discussed, the ductility or the moment curvature will depend on the axial load. So you can increase or decrease, right? Now it's set to 0. Maximum strain. How much strain do you want to consider while plotting or trying to find the moment curvature? Actually, you will find in this program that many times you will get very funny curves or no curve at all, because it is not always possible to find a solution. This is not guaranteed. So moment curvature curve solution may not be always possible, and sometimes it may give you funny results if you choose wrong data here. So maximum strain, how much you want the maximum strain to be in compression. So right now it is set to 0.008 or something. So that is the, and then strain increment, how fine you want to try the solution, right? Because it's quite possible that in an iteration you might miss the solution. So you can refine the strain increment. And if strain increment is refined, the curve will be refined. If not refined, the curve may not be so good. So these control the curve. Then controls how to stop the solution, because it's trying to find the solution. It has to stop sometimes. If you don't let it stop, it will continue forever trying to find the solution. So the stopping point is number 1, maximum strain is reached. So you stop when your maximum strain is reached and do not plot anymore, or do not search anymore, or any part of the section fails. That means either concrete or steel fails, stop. So all sections, all parts fail. That means the concrete must fail, steel must fail. Try until everything fails. Then the first rebar fails, bottom tension, or all rebars fail. So depending upon that, you can actually search the solution, what you're looking for, and draw the moment curvature according to your particular requirements. And this is a very comprehensive program to study many things. It's more like a research program. And then you can select which part of the section should fail. Because if the section has many parts, concrete, steel, composite, many things, you can choose which should fail first. Then there are some other options, curve points and so on, and then you compute. So that is the curve you will get. And you will see that when I show you the program demonstration, that when you change that, the program will change, the curve will change. Okay? So this is a very important tool to draw moment curvature curve. But what can we get from this curve? That is more interesting. That we can draw the curve, so what? By the way, look at the curvature units. It is 1/1000 per inch. So it has no units actually. So it's a ratio, right? But it's multiplied by 1000 already. So when you say 0.2, it actually means 0.0002. Otherwise you cannot see it. Output from the MV curve, that is the important thing. The first output, of course, is that you can get the yield point. The first point, when you see the change in slope, that is a yielding point, the first one. Before that, it is elastic. Cracking will be somewhere here. Second point, the last point, is the failure point. So obviously you can get two important points from this curve. But this is not all. And you can also get ductility from here. From failure point to yield point, curvature at that point divided by curvature of this point, you can calculate the ductility ratio. Right? So three things you can get directly from this curve. Then number 4, very important, you can get the stiffness of the section at any given moment or curvature, because there is a relationship between curvature and moment. So curvature is equal to moment divided by stiffness, correct? So moment divided by EI. Now in this case, we do not need to calculate the crack section properties or equivalent E or anything. We just calculate the combined multiplier of E and I, and that is stiffness. So we do not need to calculate the stiffness of concrete E value anymore. We do not need to calculate the moment of inertia of the cross section. Directly, the curvature, if curvature is known, then for any given moment, stiffness is known. Or if the curvature is known, for any stiffness, moment can be known. So that curve gives you the ability to calculate stiffness. And this is very, very important, because this information can be used for nonlinear analysis and for determining deflections and many things, because stiffness is what you need. Slope of the section at a given moment. From this equation, you can determine the slope and you can determine the deflection also. Because deflection, stiffness, slope and deflection, one by one, each one is integral of the other. So we can get the slope and we can get the deflection. And we can also get the strain at a given moment. 7 important information that you could not calculate otherwise at all by any other means easily can be computed by moment curvature curve for any cross section, any number of materials, any shape, any rebars, doesn't matter, right? And that is the strength or the benefit of moment curvature relationship. And again, I am always surprised, this is one of those hidden treasures which nobody knows, right? Engineers are not familiar with this very valuable information that can help them a lot. So now you know that you can use this for doing a lot of stuff. Crack width also can be calculated, because if you know the neutral axis depth, you know everything, you can also calculate crack width as long as you know the crack spacing. Or crack spacing can be calculated for a given crack width. So 9 items can be determined by that curve for any given loading condition. Given P, given moment, you can get everything that you need for that condition, which you cannot get from moment interaction surface that we generated before midterm, right? So that's why it is very important to understand moment curvature curve and to be able to draw it by yourself and through the program. So that is the overall diagram of how you can get all this information from MFE curve. Moment curvature curve, determine curvature for known given moment, from that. So this is the tree that you can use to make good use of the moment curvature. And what is not shown here is the hinge properties. Now the next section is, you have already seen this, I'm going to go a bit fast. You can read this in the notes, nothing new in this part, just for you to see so that you are able to read these notes, and then I will show you the program a little bit. So just to explain how this one for a beam, particular beam. So you can calculate the ductility, and this is the manual method for doing that. How you will do that, section, strain, stresses, and how you calculate that. At first you can calculate this by hand. So these are the manual calculations that you should be able to do, and you can confirm it by the program and later by test. So you have this wonderful opportunity to do something by hand, by program, by test. So please go through this, read this carefully, and use this for your calculations, right? Ductility, everything can be calculated from these equations. And then you can study what is the effect of compression reinforcement, tension reinforcement. Of course, you are not going to do that by yourself, but based on the same equations, we can study how changing compression reinforcement will change ductility. So these curves show you that if you change the compression reinforcement to tension reinforcement ratio, nothing, and then going up to 0.75, how the ductility and how everything increases. So these are the studies that people have done just to confirm what we already know, that by increasing compression reinforcement, ductility can increase. And also important is this point on the curve. If the reinforcement ratio, tension reinforcement ratio is small, curvature and ductility is large, as you keep increasing the tension reinforcement, it drops because the failure moves to concrete. Right? So this is just to confirm what we already have learned last time. Unconfined beam section, it just shows you a lot of curves proving the same point again and again. Columns now. Column is the same as a beam, except that it has axial load. Remember that, right? Integrate thing, same concept, everything is the same. Just that P is not zero, P is something. But it doesn't matter because our formulation already includes P as a variable, so you can increase P. Now what is interesting is that the curvature capacity decreases as the P increases. So it is maximum when P is equal to 0, and it tends to go like that and becomes almost 0 as the P becomes axial compression controls the failure, right? So as this is a P curve, P over P naught curve, and then as we go up, the ductility or the curvature capacity decreases until we have no more left, right? And that is why in many codes and in many places they do not want you to load the columns more than 40, 30, 40, 60%. Otherwise the ductility becomes too small, right? So the columns have to be, you have to leave some margin for ductility. But that's a problem because the architects and clients want the column to be as small as possible. So what we want and what the client wants, what the architect wants is totally opposite. We want columns with low reinforcement, low concrete strength, large size. They want column smallest with highest concrete strength with lot of reinforcement, right? So we are always in trouble with that. So what is the solution to such problems, by the way, as an exercise? What do you think? If you are caught in this situation, what do you do?
We can include ductility by other methods.
Like, for example,
Providing transfer.
transverse reinforcement is one idea. That's good. Confinement can be increased. But that again has a limit. Whatever you do, axial load will still be a problem. But true, we increase the confinement as much as possible, go to the maximum. And then, good idea. What else can we do? We try not for the columns to yield, or we reduce the ductility demand on the columns. We design the structure in such a way that we do not need ductility from columns. That is always the thing that you should do. If you have a problem, solve the cause of the problem. Because if you try to solve the problem at hand, you may not be able to solve it. You need to go back. So if your columns cannot have ductility, find a way that you do not need ductility in columns. Right? So reduce the demand if you cannot increase the capacity. It's as simple as that. It's a demand and supply problem. If you cannot supply ductility, reduce the demand. And how do you reduce the demand? Move all the ductility demand to beams. Let the beams take all the ductility because they don't have a problem with the axial load. So let the beams yield first. Let all the ductility and energy absorption come from beams, not from columns. Keep the columns elastic. And that is why the ACI code and other codes which are dealing with this one say strong column, weak beam design. Make the columns strong, make the beams weak. Let the beams yield first. So they will yield, they will reduce the demand of earthquake because many effects. So basically you move the demand, ductility demand from columns to beams, which is easy to provide ductility. That is why we are studying both columns and beam. So if you cannot have high ductility in columns, design in such a way that beams take the ductility first. Clear? Okay. This is always the rule. Always look for a solution that is to solve the problem at the source. Do not let the problem come and then solve it. And this is the effect of, because the axial load, we already have seen it. If you increase the axial load, the ductility will reduce. So we know that. Confined, now same thing. So moment relationship and ductility are related, as you know very well. Effect of axial load, we have to study that. We can play with that. Effect of reinforcement ratio, we can play with that. Tension and compression. The problem with column is that we do not know which one is tension, which one is compression reinforcement. Each direction can be tension or compression depending upon the direction of earthquake or wind. So that means you need to have a uniform distribution of reinforcement, because each side can be compression or tension. So compression and tension ratio is 1 always in columns. So that is one consideration to be made. Second is that the axial load is going to reduce your ductility. Now, one thing interesting is, in a column, in a building, not all columns have the same axial load ratio. What does that mean? It means that the architects sometimes want the same column size everywhere. Some of them will have high loading, some may not have high loading. So you can identify those columns and you can put more ductility in them than the other columns. So you can design or distribute your ductility looking at the axial load distribution of the columns in the building. So it needs careful thinking of how you are going to, so basically you can instruct your structure to behave in a certain way by using the concept of these concepts. Effect of compression, steel, we already talked about. Effect of confinement model, we talked about a lot. So now this is not something that up to you, because just because you choose a certain confinement model, it doesn't matter, the reality is changed. It's only your analysis which has changed. So you need to select a confinement model which is closest to reality, because you cannot change numbers by simply choosing another model. That is cheating, kind of, right? But sometimes we don't know which model is correct. So, but in any case, we have to see which confinement model to use, which is most realistic for that particular cross section, right? Okay. And then effect of confinement shape, we already talked about a lot. This is a comparison from the program that I'm going to give you. Left hand side is a ACI Whitney block, not confined. Right hand side is the same cross section, same reinforcement, same everything, just change the confinement model and put some confinement there, and you get the Bender confined model. And please see the number. Here at about 0.6 curvature, it failed. Here it failed at about 3.5, right? So how many times? 5 times you could increase the ductility by using some confinement here and using the right model, right? Of course, you need a program which can do all of that, but you can clearly see that the moment capacity did not change significantly. It changed a little bit from about 900, it went to about 1000 or something, but the point is that it had a ductility up to about 3.5. Here it finished at around, in fact, 0.5, not even 0.6, 0.5, so about 6 times, right? After that failed suddenly. This one also failed, and this, of course, it depends how far we go and what we do, but we normally do not cross this line, right? This final point. So the main thing that we can learn from here is that we can improve the ductility of the cross sections by using the confinement, and more importantly, considering that confinement in our analysis. If the model does not allow you to consider the confinement, then it will not give you the right numbers. So this is the study about axial load and ductility. This is coming from that thesis that I mentioned to you. It was done by one of the students, so you can see what he plotted. Some other numbers we have already seen. Steel ratio. As we increase steel ratio, ductility becomes less, capacity increases. So it's a compromise between capacity and ductility. Sometimes we can increase the strength so much that you don't need ductility, or you can reduce the strength and use ductility. So it's always a compromise between the two. You can either make it so strong that you don't need ductility, or you make it weak but use ductility. So combined, this two, you need to play with those two numbers. Compression steel, we have already studied this, a lot of slides on that. This is from that student, he studied, this is from section builder, he studied 8 bars here, 8 and 2, 8 and 4, 8 and 8, and draw these curves and see the ductility. For this one goes very high, very large ductility, right? Confinement models, the one that we just looked at, we also looked at those different bender. The best one, of course, is concrete filled tubes. It just goes on very long. Confinement spacing, shape. So strategies to improve ductility: use low reinforcement ratios as possible, add compression reinforcement as much as possible, add confinement reinforcement, right? That's how you manage ductility. And all of that can be studied through moment curvature curve. Other factors, the advantage of using confinement, indirect advantage is that reinforcement also becomes useful for shear and increases the shear capacity automatically. So same reinforcement that you use for confinement also increases the shear capacity. Prevents buckling of bars, longitudinal buckling of bars, because the spacing is small. So it also improves the overall integrity of the section. Prevents bond splitting failures, because at the bond splitting, it does not allow the bars to separate. So by using confinement or transverse reinforcement, you get a lot of benefits. Confinement and free shear, free these three. These things come free, right? So that's why it is always good to consider the transverse reinforcement carefully. Now we come to an interesting topic, which you are doing a lot, or going to do a lot for your class project. We are planning to design a beam in which the moment will redistribute, because elastic moments will be different, and we are going to redistribute the negative positive moment after yielding. So this is what is called moment redistribution and plastic hinging. Plastic hinging means that the material becomes plastic. It starts to flow, it starts to bend without breaking, like a plastic. So limit design means that you limit the moments at certain locations and allow the moments to jump to another location. So this is called a limit design, or limiting design, or moment redistribution, or moment capacity-based design. You can call it many ways. Basic idea is that you allow the cross sections at some locations to have capacity less than what the demand is going to be. Allow them to yield, deform but not break, so that moment can go somewhere else, right? That is the whole idea behind this approach of moment redistribution. And moment redistribution is very useful. It has been there for a long time in the codes, but people never really understood what it is. For example, British code, ACI code, they allow 15% moment redistribution. That means if you calculate a moment, negative bending moment, let's say 100, you can make it 85 and move that 15 to positive as long as the sum of the total moment is still the same, right? So that way you can reduce reinforcement congestion, because normally at the top of the beam there's a lot of rebars. If you cannot fit them, you take out some bars and put them at the bottom and let it yield, right? So that is coming from this concept that we are talking about, yielding. So the only concern is cracking. When you allow the member to yield, it will crack. Now for you and I, cracking may be okay because we know that cracking doesn't mean failure. Go tell you're at home, in your living, and your beam cracks, and your mom or your sister or somebody sees it and says, oh, the house is falling down, it's cracking. For public, it is unacceptable. They cannot understand that cracking is normal, right? If you tell them that we design for cracking, they say you're crazy. Why don't you design that does not crack, correct? So cracking, although not harmful structurally, serviceability and appearance and perception is changed. That's why we allow cracking on the top of the beam, which is normally hidden by the flooring, so no one can see. And then we normally allow cracking to happen for dead load before finishes. So that means after finishing, there should be no cracking, something like that, right? So those kind of things can help to control this phenomenon. I don't know how many projects we have investigated where the clients call us that please come and look at the cracking in our building, beams and slabs. It's so common, so many buildings develop cracks, and sometimes excessive cracks, not well managed, not intentioned well. And many times those cracks are coming from anyone. If you see cracking in slabs especially, what could be the most common cause? Yes, yes. Yes, good. One more. Temperature. Temperature and shrinkage are the two most common causes of cracking, which most of us do not study well. We do not understand well. But those are the ones that we miss, and those are the ones that cause cracking. They combine with the other stresses and cause cracking. And all of the code equations for minimum reinforcement do not really work well. Anyway, that's another topic we will discuss some other time. So this is what we are talking about. You have a bending moment, you have a beam like your beam, and you get this bending moments, negative, positive, and then you can move it up and down this moment diagram in such a way that you can control the bending by yourself by putting hinges, and that is what you are doing. You are actually putting hinges. Your beam is like this, right? One span of this beam. So you have 3 hinges, 1, 2, 3 hinges. You are going to control these hinges to control the bending moments, right? And redistribute them as you want them. So in your case, positive moment is larger than negative moment, correct? So you will see first yielding at the bottom, and then moment will reduce at the bottom. It will go to the negative moment will increase, and then they will yield, right? Something like that. So the yielding sequence should be positive yielding followed by negative yielding, correct? Because you have uniform reinforcement everywhere. So we should observe all of that and see how it comes. So this diagram, initial elastic diagram and plastic diagram will be different, and we need to study both. What is the moment diagram after yielding? And how can you calculate moment after yielding? From moment curvature, from strains that you are going to measure, because curvature and strain can give you corresponding moment. So this is all about that. You can read. These are the guidelines for providing confinement and shear in beams. These are the confinements for providing confinement in columns. Sometimes we also need to do this, strengthening. old section or old section, new section around that, old section, new section. So sometimes we need to do retrofitting. That means you find a investigated building, pest is not enough, you add something to it, either jacketing or whatever, and then you need to calculate the capacity again, and that is that when the codes do not help you. All right, thank you. So this concludes the discussion on, before I open the program, any questions? One thing that I did not tell you yet, hinge length. We talked about moment curvature. We did not talk about moment rotation, right? In the previous one of the slides, you need to multiply the curvature by a certain length to get the rotation. That means curvature is one section, but if you add up all the curvatures on a certain length, it will become rotation. And that length is called hinge length. Typically, hinge length is equal to the depth of the beam or column. So if you multiply the curvature by the length, then it will become rotation. So you can plot moment rotation, and hinge length is typically equal to depth of the beam. So you can also calculate moment rotation curves. It's the same as moment curvature, just multiply the curvature by the length h, right? It becomes moment curvature. It's the same thing, just a different way of looking at it. Okay, let me show you the program for a few minutes so you get some idea. So it is a little bit small, you may not be able to see it, but this is how the program looks like. So there are a lot of ways that you can create a cross section by defining from all these shapes, or you can get the cross section from libraries. There are many libraries, basic libraries from here, or there are libraries like that, shear walls libraries, here, column here. So hundreds of cross sections are already defined there, or you can create your own cross sections, and so you can play around. This program is like, and also bridge sections, so you can study all of those sections by using a parametric definition. Let me just do a very simple one. Let's say a T section. And if you double click this one, you can go here and you can change the dimensions. Let's say 12. And refresh. Oh. And then you can add bars here. So you can draw bars anywhere. Of course, this is not so good, so select that and distribute, right? So you can draw and then you distribute around the edges, and then you can specify what material model you need. Mender, another. You can use any of the available concrete models, and you can study that. And these are the properties that you get, and you have added the rebars, so you say okay, this comes here. And then you can draw the inflection curve. So that is the inflection curve for that T section. And you can change the angle. This is 0 degrees, 90 degrees, 30 degrees, and so on. You can also look at the surface. So you can see that this is the surface of a T section. You can also look at the PM diagram. And this is what I told you last time. The PM diagram at different loads will look very different. So if I change the load to be that, it becomes like that. And this one. So it keeps changing depending on the P value. So you can specify the P value. And you can generate the moment curvature curve. So that's the moment curvature curve for that column. And by specifying these things, first bar yields. So it stops here, just like that. That means you only, as soon as the first bar yield, you stop the curve. But here we say maximum strain is reached, so it goes until it can go, right? And then you can specify many things from this one to study the moment curvature curve for any section and any shape. And you can apply the loading and so on and so forth. One thing interesting here is here. You can actually watch how the reflection surface is being generated, or the program is using changing the cross section every time and generating the reflection surface by rotating the cross section and generating every time, rotates the cross section, change the new plexus depth, calculate the points, rotate again, and every time you see the new plexus changing and section rotating, and every time one curve, one point is being generated. So this is how the program is. I just put some animation to show how the program generates that surface. And then you can view the generated surface, which is here. Right? So that procedure generates the surface. You can also add shapes here. For example, we can add a circle and maybe move that here, and then select both of these and try to merge it. So the shape can be merged together to create more complicated shapes. So you can almost create any shape that you need by combining different shapes, by merging, and then adding rebars. So if you double click this one, then you can add rebars here further. So you can create different shapes, and different confinement models can be, and you can also place, for example, steel shape inside. So you can create a composite section with steel shapes and any kind of, and then you can generate all of those curves. So this I can assure you that this is probably the world's most powerful cross-section design program that you can find that can do all of that and then generate the stresses and everything. You should be able to see, I hope it works, the stresses. Yeah. So you can see the stress diagrams. Last time you could not see. So you can see the moment, you can see the shear stress, you can see other stresses for loading. Right? So you can study how the shear stress will change, torsion stress will change, and pre-stressing will change, right? All of that. Okay, so this program I will put up. Use that, get familiar, because it can solve almost all cross-section issues that you may have, design and investigation analysis issues. All right? Any questions? So this we finished cross sections, flexure, shear, torsion, curvature, ductility is done.